A ceramic is an inorganic, non-metallic solid material comprising metal, non-metal or metalloid atoms primarily held in ionic and covalent bonds. The crystallinity of ceramic materials ranges from highly oriented to semi-crystalline, and often completely amorphous. Varying crystallinity and electron consumption in the ionic and covalent bonds cause most ceramic materials to be good thermal and electrical insulators and extensively researched in ceramic engineering. Nevertheless, with such a large range of possible options for the composition structure of a ceramic, the breadth of the subject is vast, and identifiable attributes are hard to specify for the group as a whole. However, generalities such as high melting temperature, high hardness, poor conductivity, high moduli of elasticity, chemical resistance and low ductility are the norm, with known exceptions to each of these rules. Many composites, such as fiberglass and carbon fiber, while containing ceramic materials, are not considered to be part of the ceramic family. The word ceramic comes from the Greek word kappa epsilon rho alpha mu iota kappa omicron sigma, of pottery, or for pottery, from kappa epsilon rho alpha mu omicron sigma, potter's clay, tile, pottery. The earliest known mention of the root ceram is the Mycenaean Greek ramiwi, workers of ceramics, written in Linear B syllabic script. The word ceramic may be used as an adjective to describe a material, product or process, or it may be used as a noun, either singular, or, more commonly, as the plural noun, ceramics. The earliest ceramics made by humans were pottery objects, including 27,000-year-old figurines, made from clay, either by itself or mixed with other materials like silica, hardened, sintered, in fire. Later ceramics were glazed and fired to create smooth-colored surfaces, decreasing porosity through the use of glassy, amorphous ceramic coatings on top of the crystalline ceramic substrates. Ceramics now include domestic, industrial, and building products, as well as a wide range of ceramic art. In the 20th century, new ceramic materials were developed for use in advanced ceramic engineering, such as in semiconductors. Types of ceramic products. By usage for convenience, ceramic products are usually divided into four main types. These are shown below with some examples. Structural, including bricks, pipes, floor and roof tiles. Refractories, such as kiln linings, gas fire radiants, steel and glass-making crucibles. Whitewares, including tableware, cookware, wall tiles, pottery products and sanitary ware. Technical, also known as engineering, advanced, special, and fine ceramics. Such items include gas burner nozzles, ballistic protection, nuclear fuel, uranium oxide pellets, biomedical implants, coatings of jet engine turbine blades, ceramic disc, brake missile nose cones, bearing tiles used in the Space Shuttle program. Ceramics made with clay. Frequently, the raw materials of modern ceramics do not include clays. Those that do are classified as follows. Earthenware, fired at lower temperatures than other types. Stoneware, vitreous or semi-vitreous. Porcelain, which contains a high content of kaolin. Bone china. Classification of technical ceramics. Technical ceramics can also be classified into three distinct material categories. Oxides, alumina, beryllia, ceria, zirconia. Non-oxides, carbide, boride, nitride, silicide. Composite materials. Particulate reinforced, fiber reinforced, combinations of oxides and non-oxides. Each one of these classes can develop unique material properties because ceramics tend to be crystalline. Other applications of ceramics. Knife blades. The blade of a ceramic knife will stay sharp for much longer than that of a steel knife, although it is more brittle and can snap from a fall onto a hard surface. Ceramic brake discs for vehicles are resistant to abrasion at high temperatures. Advanced composite ceramic and metal matrices have been designed for most modern armored fighting vehicles because they offer superior penetrating resistance against shaped charges and kinetic energy penetrators. Ceramics such as alumina and boron carbide have been used in ballistic armored vests to repel large-caliber rifle fire. Such plates are known commonly as small arms protective inserts, or SAPIs. Similar material is used to protect the cockpits of some military airplanes, because of the low weight of the material. Ceramics can be used in place of steel for ball bearings. Their higher hardness means they are much less susceptible to wear and typically last for triple the lifetime of a steel part. They also deform less under load, meaning they have less contact with the bearing retainer walls and can roll faster. In very high-speed applications, heat from friction during rolling can cause problems for metal bearings, which are reduced by the use of ceramics. Ceramics are also more chemically resistant and can be used in wet environments where steel bearings would rust. In some cases, their electricity insulating properties may also be valuable in bearings. Two drawbacks to ceramic bearings are a significantly higher cost and susceptibility to damage under shock loads. In the early 1980s, Toyota researched production of an adiabatic engine using ceramic components in the hot gas area. The ceramics would have allowed temperatures of over 3,000 degrees Fahrenheit. The expected advantages would have been lighter materials and a smaller cooling system, leading to a major weight reduction. The expected increase of fuel efficiency of the engine could not be verified experimentally. It was found that the heat transfer on the hot ceramic cylinder walls was higher than the transfer to a cooler metal wall, as the cooler gas film on the metal surface works as a thermal insulator. Thus, despite all of these desirable properties, such engines have not succeeded in production because of costs for the ceramic components and the limited advantages. Such engines are possible in laboratory settings, but mass production is not feasible with current technology. Work is being done in developing ceramic parts for gas turbine engines. Turbine engines made with ceramics could operate more efficiently, giving aircraft greater range and payload for a set amount of fuel. Recent advances have been made in ceramics which include bioceramics, such as dental implants and synthetic bones. Hydroxyapatite, the natural mineral component of bone, has been made synthetically from a number of biological and chemical sources and can be formed into ceramic materials. Orthopedic implants coated with these materials bond readily to bone and other tissues in the body without rejection or inflammatory reaction, so are of great interest for gene delivery and tissue engineering scaffolds. Most hydroxyapatite ceramics are very porous and lack mechanical strength, and are used to coat metal orthopedic devices to aid in forming a bond to bone or as bone fillers. They are also used as fillers for orthopedic plastic screws to aid in reducing the inflammation and increase absorption of these plastic materials. Work is being done to make strong, fully dense nanocrystalline hydroxyapatite ceramic materials for orthopedic weight-bearing devices, replacing foreign metal and plastic orthopedic materials with a synthetic, but naturally occurring, bone mineral. Ultimately, these ceramic materials may be used as bone replacements or with the incorporation of protein collagens, synthetic bones. High-tech ceramic is used in watchmaking for producing watch cases. The material is valued by watchmakers for its lightweight, scratch resistance, durability and smooth touch. IWC is one of the brands that initiated the use of ceramic in watchmaking. The case of the IWC 2007 Top Gun edition of the Pilot's Watch double chronograph is crafted in black ceramic. Types of ceramic material. A ceramic material is an inorganic, non-metallic, often crystalline oxide, nitride or carbide material. Some elements, such as carbon or silicon, may be considered ceramics. Ceramic materials are brittle, hard, strong in compression, weak in shearing and tension. They withstand chemical erosion that occurs in other materials subjected to acidic or caustic environments. Ceramics generally can withstand very high temperatures, such as temperatures that range from 1000 degrees Celsius to 1600 degrees Celsius. A glass is often not understood as a ceramic because of its amorphous character. However, glass making involves several steps of the ceramic process and its mechanical properties are similar to ceramic materials. Traditional ceramic raw materials include clay minerals such as kaolinite, whereas more recent materials include aluminium oxide, more commonly known as alumina. The modern ceramic materials, which are classified as advanced ceramics, include silicon carbide and tungsten carbide. Advanced ceramics are also used in the medicine, electrical and electronics industries. Crystalline ceramics. Crystalline ceramic materials are not amenable to a great range of processing. Methods for dealing with them tend to fall into one of two categories: either make the ceramic in the desired shape, by reaction in situ, or by forming powders into the desired shape, and then sintering to form a solid body. Ceramic forming techniques include shaping by hand, slip casting, tape casting, injection molding, dry pressing, and other variations. Details of these processes are described in the two books listed below. A few methods use a hybrid between the two approaches. Non-crystalline ceramics. Non-crystalline ceramics, being glass, tend to be formed from melts. The glass is shaped when either fully molten, by casting, or when in a state of toffee-like viscosity, by methods such as blowing into a mold. If later heat treatments cause this glass to become partly crystalline, the resulting material is known as a glass ceramic. Widely used as cooktop and also as a glass composite material for nuclear waste disposal. Ceramics in archaeology. Ceramic artifacts have an important role in archaeology for understanding the culture, technology and behavior of peoples of the past. They are among the most common artifacts to be found at an archaeological site, generally in the form of small fragments of broken pottery called sherds. Processing of collected sherds can be consistent with two main types of analysis: technical and traditional. Traditional analysis involves sorting ceramic artifacts, sherds and larger fragments into specific types based on style, composition, manufacturing and morphology. By creating these typologies, it is possible to distinguish between different cultural styles, the purpose of the ceramic and technological state of the people, among other conclusions. In addition, by looking at stylistic changes of ceramics over time, is it possible to separate the ceramics into distinct diagnostic groups. A comparison of ceramic artifacts with known dated assemblages allows for a chronological assignment of these pieces. The technical approach to ceramic analysis involves a finer examination of the composition of ceramic artifacts and sherds to determine the source of the material and through this the possible manufacturing site. Key criteria are the composition of the clay and the temper used in the manufacture of the article under study. Temper is a material added to the clay during the initial production stage, and it is used to aid the subsequent drying process. Types of temper include shell pieces, granite fragments and ground sherd pieces called grog. Temper is usually identified by microscopic examination of the tempered material. Clay identification is determined by a process of refiring the ceramic, and assigning a color to it using Munsell soil color notation. By estimating both the clay and temper compositions, and locating a region where both are known to occur, an assignment of the material source can be made. From the source assignment of the artifact, further investigations can be made into the site of manufacture.